I'm Dave Fashionpour from Instructional Math Tools in West Melbourne, Florida. This presentation will explain to you how I am able to do three-dimensional Mandelbrots. People say you can't do that. I'll explain to you how I can. The following presentation will discuss William Rowan Hamilton's position by saying you cannot establish an R3 field, and it will explain why I say you can do it by sharing with you my little 3D secret. And then lastly, we will pick some complex points and we'll plot them in the 2D and in the 3D environment. The answer is no from William Rowan Hamilton. He said, you're asking me to make a space R3 into a field by extending the field structure of C onto R. Spent most of his life trying to make sense out of an R3 field structure. But in 1850, he declared that he can't do it. And he turned directly to a 4D solution, quaternions. It didn't give him exactly what he wanted with regard to commutative multiplication identities, but it was close enough, while at the same time produced an extraordinarily important mathematical tool. But with regard to R3, no, there's nothing you can do that even can come close. Now, to understand that, we first have to understand what he was talking about. This is an example in the 2D environment, how you can make sense out of a field, out of an R2 field. You take a complex point, 2 plus 3i, and you multiply it times I, and it flips it over to the next quadrant 90 degrees. You multiply this point times I, and it flips it, so on and so forth. So you can see for yourself, this makes sense. This is a field. This is a field that shows a relationship between reals and imaginary numbers. This is what he was talking about. He couldn't get this kind of activity going in a 3D environment. In this environment, all he had to do was worrying about binomial multiplication. And given a 2D commutative identity, multiplication identity, such as I times I is -1, everything worked quite well. He gave up because he couldn't multiply triplets. Every morning his son would say, "Papa, can you multiply triplets yet?" And every day he would respond to his son, "No, not yet." And one of the problems, of course, was he was multiplying triplets, trying to use a multiplication commutative identity setup that didn't work. It didn't seem to flow in a field like the two-dimensional did. So he said, I can't do it. Let's turn to this, which was an extremely important decision, but one that left this one hanging loose, which we'll talk about in a minute. What happens when a complex number is submitted to Mandelbrot's recursion? Turns out that only three things can happen. Either the signal comes back and it's a reject, and you're supposed to ignore this number and not color it any color at all. Or it comes back to be a fractal and you can color it anything you want. Or it comes back as a set member and that belongs to Mandelbrot's set C, and that color of this point becomes black. Those are the only three things that can happen out of Mandelbrot's recursion. You submit a complex point to it. It's got a real and imaginary side to it. submit it to the recursion. There's squaring of binomials going on in there, and there's a boundary circle of radius 2 that's used to determine whether the cycle is to be terminated or not. And we have chosen just randomly 40 loops to be the downside and 1,000 loops to be the high side. These are negotiable and arbitrary, but this works rather well. And once you assign those, then you can determine whether the signal coming back is a reject, a set member, or a fractal. Notice there are no complex number coordinates output from the recursive box, only one of 3 status indicators. Ignore black or any color. The key here is that there is no field translation necessary, because there is no field that is a part of this process. The only thing that's a part of this process is squaring binomials. Inside, what happens is that new points are calculated. Given the point C, there's a series of binomial multiplications that occur that produce a point 2. Some more binomial multiplications that occur to produce a point 3, and so on and so forth. And as soon as those points jump out of the circle of radius 2, then it's a reject, it's a termination, and you record the number of times it looped within the circle. If it's less than 41, it's a reject. If it looped greater than 1,000 or equal to 1,000, then it's a set member. And if it looped greater than 40 but less than 1,000, it's a fractal. And all of these binomial multiplications utilize the 2D commutative multiplication identities as we discussed earlier. Now, what is the difference between a 2D and a 3D? In 3D, you need commutative identities, and I have copyrighted this set right here to say that if you're going to do some multiplication of triplets within this 3D recursion, you need some identities, and here is the set of identities, just like the ones we needed for 2D. This is the one needed for 3D. And so when you go from point C, you multiply some triplets, and you get a point 2, and a point 3, and 4, and so on and so forth. And keep in mind that nothing comes out of this box that has anything to do with the field or anything to do with the graph. The only thing that comes out of this box is a resolution as to whether it's less than 41, or it's greater than 40 and less than 1,000 loops, or is it between this range. Those are the only 3 things that come out of this box. Hence, this is why that this set of identities is important, because it makes this 3D determination valid, in conjunction, of course, with the 2D, which still applies. What's the difference? The only difference in the Mandelbrot set with the recursive equation as outlined here, Mandelbrot assigns C as A plus BI, is exactly the same in the 3D environment, with the only difference the addition of an I prime, the DI prime. That is the only difference. And of course, when you add a DI prime, you necessitate triplet multiplication. What does that mean? 3D triplet multiplication, when you multiply this 3D point plus this 3D point plus C, which is the Mandelbrot recursive equation expanded to support 3D, you get this kind of thing. And the bottom line is that you need to multiply these two together and these two, and you have to remember that there's some identity issues going on here that you wouldn't have in normal arithmetic. Same here. We have to follow the identities as defined in 3D. And once you do this, once you determine square 1, square 2, square 3, cross 1, cross 2, and cross 3, once you've done this, then all you have to do is follow this rule here that says the real part of the newly calculated point is square 1 plus square 2 plus square 3 plus cross 3 plus a2. a2 is the original C, real part of C that was submitted to the recursive equation. The imaginary part is determined by taking cross 1 and adding it with b2, which is the imaginary part of the C, the point C that was submitted to the recursive equation. And for the extended imaginary part, the I prime, you take cross 2 and you add it to d2, and of course d2 is the extended imaginary portion of point C. And once that is accomplished, you have created a new point. You were given a point, now you've created a new point, and that point is evaluated with regard to a border test, and however many times it loops before it fails determines what kind of point it is. If it passes, it keeps looping, it gets another point, get back to the border test, another point, get back to the border test, back, keeps looping as long as it keeps passing and not jumping out of the circle of radius 2 until it fails. And then then you know how many loops that it occurred, and it tells you what kind of point it is. Let's plot some points in the 2D environment to utilize Mandelbrot's recursive equation. This is a actual output of a tool that I wrote that responds with the status. Given a point, it comes back with the status and tells how many loop counts that occurred, and then we know what kind of point it is. Well, the first point we're going to use is this one, which points to the black, actually, to the outside of the circle. So we've already jumped the circle, and we feed that information to this tool, and the tool comes back and says it's a reject, starts outside of the circle of radius 2, loop count is 0. You can forget all about that point. We can ignore it. It doesn't matter. It's not legal. Okay, the next point we're going to submit is not into the fractal area of the baby, and it's not into the set membership area of the baby. It's still in the white. It's within the circle, but it's out here in the white. That's the coordinates. We submit those coordinates to the tool that calculates what Mandelbrot's 2D equation comes out to be, and it says it has a boundary violation. It jumped the circle of radius 2 at 40. Well, if your loop count is 40, that means your background. Well, that's exactly what we thought it would get. It's the white background. And one thing I want to point out here, if you'll notice, we have an X value and a Y value, but the Z value has been set to 0. The reason for that is my tool accounts for 3D, but we're not utilizing the 3D aspect yet. Everything on the Z axis is set to 0, making it all two-dimensional. At this point here, we're starting to get into the fractals. You notice this little nodule here, we're going to be looking closer and closer at it, but right now we're approaching that nodule and we're into the fractal area. When we submit those coordinates to the tool, it comes out to tell us that it's cycled for 41 cycles and that it is truly a fractal. It is qualified to be a fractal, and it can be any color you want it to be. Let's try another one. This one is down a little bit, still in the fractal area, and we submit that point to the, and by the way, this is the first 40 recursive iterations that are listed here. The others are ignored because it would go on forever. So we just show the first 40. In fact, we even remove some of the 40 right in here. But this is just to give you an example of what happens. And the output here has had a border violation at loop count 100. Well, what does that mean? Well, loop count 100 is still a fractal. Okay, it's less than 1,000, so, and it's more than 40. So it's still a fractal. We're still playing around with this nodule here. Let's try another one. This one here, it's not into the black here, but it's into the lower level fractals, way below that nodule. We submit that. What does it tell us? Loop count of 500. It's not 1,000 yet. Getting close, but it's 500 and it's still a fractal. Okay, let's submit another one. This one here is intentionally into the black part of that nodule. So it doesn't take a lot, just a little bit of adjustment from fractal into the nodule. We feed it in, and guess what? Loop count is 1,000. It is a Mandelbrot set member. End of story. Okay, now let's try something different here. We are going to view this little nodule we've been looking at in a three-dimensional mode here. And we're going to ask the question, what happens when we exercise the z-value here, right? We haven't been messing with the z-value here. If z were 0, like it is there, it's a Mandelbrot set member, and the loop count is 1,000, and we're sitting right where we were. But now we're going to put some values into z and see what happens. So this time, this little thing is coming out. So it's coming out at you here by 0.001. It's coming this way. And when you feed negative 0.999, positive 0.287, and then you assign a z-value of positive 0.001, positive meaning it'd be coming out this way, then the outcome is a loop count of 114, and it's a fractal. So that's interesting to note that as we come out from that two-dimensional plane and we're coming out at you, you encounter a fractal. Very interesting. All right, let's add one more. Let's 0.002, coming out that far. What do we get? It's a fractal. Let's do it again. We're coming out at you, coming right towards you. Another 132 this time. It's still a fractal. And again, it's still a fractal. We're coming closer. It's a fractal. 41, it's getting closer to being a non-fractal here. And then 44, so it's jumped up a little bit. We're still as a fractal coming out, and we're 0.006. We're 6 thousandths of a unit out toward us. Even another one, 7 thousandths of a unit out toward us. It's still fractal. And guess what? 8 doesn't do it. 8 breaks out. 8 breaks out and turns out to be background or noise. This is like equivalent to the white circle. It's left the Mandelbrot. It's left this 3D nodule, and it's now into the gray area here. And it's called background, loop count of 36. So that's as far as that goes out toward us from that nodule in 3D. All right, let's try the inevitable here, which is instead of going out at us, let's go this way and see what happens. So we submit a 0.008, the same unit that brought us background here. Let's see what happens when we go this way. We submit that in, and it says it's a Mandelbrot set member. Now wait a minute. We were a Mandelbrot set member right here, and we're 0.8 thousandths out here, and we're still a Mandelbrot set member. What's going on here? It's not like the other side here where we got fractals. Now we got set members. That's very interesting. So let's jump ahead. Let's make it 0.1. That's quite a jump away from us, down the road here, out this way. Still a set member. My goodness, what's happening? 0.2, still a set member. 0.3, set member. 0.4, set member. 0.5, set member. 0.6, it's background. Loop count 17, went to the background. What does that say? What that says is that when we got this far, 0.6 out in this negative direction of z, going away from you, we finally reached the gray background, but it took more than a half a unit to get there. So in summary, here we have 0.57 thickness between the furthest point out here and the furthest point back here of this module. And that's got to be unusual for somebody that's never seen this before. And here's the reason why it's unusual. Because what we're looking at here is the Mandelbrot fractal log. It's a three-dimensional Mandelbrot. And we were looking at this nodule right here. And if you come out at us from right there, there's nothing to stop you. You go through a few fractals, and all of a sudden, you're out in the background. There's nothing that keeps you from reaching the background easily when you come toward us from this view. Now, if you go the other way, if you go back away from us, you go into the background of the set membership of the unit behind it. This is a series of babies, Mandelbrot babies, and they are oriented at 45 degrees. They're going up a hill here, 45 degrees. So when you go drilling down here and you go back this way, what you're doing is you're drilling into all the babies that are on that side of it until you get to the other side of the log. So it's easy to come forward here. It's easy because there's nothing there. You come out and you're free. But you go back this way, you have to drill down through set members until you get to the other side of the log. Now, this doesn't prove anything because we still have a lot to go, and we'll do that in part 2. But what this does give you an indication that this 2D Mandelbrot, when treated like a 3D figure, actually displays the same characteristics that you would expect it to display in a 3D environment. So that's all we wanted to accomplish in part 1, just to let you know that this is not a fluke. This is not some anomaly that we've uncovered. This is an actual implementation of a 3D Mandelbrot fractal log that I have copyrighted, by the way. This concludes part 1. Part 2 is learning more about the Mandelbrot fractal log. It's fascinating, and you're going to want to listen to part 2. I am Dave Fashionpour, Instructional Math Tools, West Melbourne. I have my email there, as well as my phone number. If you do call the phone number, please leave a message, because I don't answer all long-distance incoming phone calls. And if you want to see this video plus other videos, please visit fractallog.com. Thank you for your time, and we'll talk to you soon.